Hello there everybody. Welcome to the MCAT ACE lecture for General Chemistry, and in this lecture we're going to be covering the periodic table and the different element families that are found within the periodic table. So I've got an outline here to talk about what this video lecture is going to cover. Specifically, as we just mentioned, we're going to talk about the elemental families, and this is going to be broken down by valence electrons. So for instance, you go down the first row, all of the first elements would have one valence electron. The second row, two valence electrons, so on and so forth. And they all have various properties according to that, especially the metals. So we'd like to break this down into three major sections. And when you look at the periodic table, you can break it down into metals, metalloids, and nonmetals. So most people know about metals and nonmetals. However, metalloids are a very select few set of elements that sort of ride the line between metals and nonmetals, and they have unique properties that carry them in between those two groups. So for the metals, if we were to break it down, you have alkali metals, alkaline earth metals, transition metals, and then those big ones that are at the very bottom of the periodic table are known as the lanthanide and the actinide series. Those are also metals, although they are far less common in terms of their use both in studies as well as in actuality in the real world. We tend to come across a lot more of the alkali metals, the alkaline earth metals, and the transition metals. We will discuss the metalloids and take a look at them. They include things like boron, germanium, a couple others that are in there. And then the nonmetals, the most commonly known ones are carbon, nitrogen, and oxygen, including all other elements in those families. So, for instance, the carbon family would also contain silicon, the nitrogen family would contain phosphorus, and the oxygen family would contain sulfur, all of which are important elements in the human body and in most biochemical pathways / chemicals that you would come across, reagents. You then have the halogens, slightly less common, but still very, very prevalent and important, especially when you deal with chloride, because you're talking about sodium chloride, when you're taking in certain electrolytes. You also have iodine, which is another very important nutrient. And then finally, we have the noble gases all the way at the end of the periodic table. They are rather inert, and they are not reactive. So that is what we are going to be looking at during this lecture. We're going to break it down. First, we'll talk about metals, metalloids, and nonmetals and the difference between them. And then we'll take a look at some of the individual families and what would separate them or make them different from the others. So to get started, I do have the periodic table of elements down here, so we can take a look at that. It's rather large because I do want to be able to zoom in and have you see everything we're talking about. So we'll sort of scroll back and forth as we're going through this, and you can get a feel for what we're talking about and where we are. So the first major topic is metals, metalloids, and nonmetals. So when you take a look at the metals, most of the periodic table is comprised of metals, a very large portion of it. So everything you see on the left over here, starting with hydrogen. So if you were to take a look at this portion right here, the hydrogen in blue, and everything from there over to around this area here with boron, and even some parts of this, you can see the aluminum, the gallium that are underneath boron, those are considered metals as well. So everything in that chunk of the periodic table is going to be considered a metal, including, as we mentioned before, if you come down here, they have a tendency, if you take a look at the area that says 57 to 71 and the area that says 89 to 103, those are removed from the periodic table and they are brought down into this larger portion here. Okay, this is known as the F block. It's talking about the F shell. So if you remember your shells, you've got S, P, D, and F, which we will talk about during this video. But if you take a look down here, the F shell, the top one is the lanthanide series, and the bottom one that's in red here is the actinium series, or the actinide series. And those are metals as well. Again, a little less common, but there are important metals in there. Probably one of the best known ones is uranium, when you start talking about radioactivity and things like that. All right, so coming back up, that's a large chunk of the periodic table, because if I move over and I take a look here, that leaves only this small little portion. It's still somewhat sizable, but this portion over here to the right is going to be the nonmetals. The metalloids, and there's some debate on what is technically a metalloid and what's not, because the properties are the dividing lines here between the metals and the nonmetals. But you can see boron, silicon, germanium, arsenic, antimony, tellurium, and polonium, and sometimes even this one that's at the bottom of the halogen row right here, the actinide, is also considered at times to be a metalloid, depending on who you ask and the classification. And then mostly what's over here are the nonmetals that we would certainly consider to be nonmetallic. Things like oxygen, chlorine, which is a gas when it's not in its ionic form, bromine, which would be a liquid, the noble gases, helium, neon, argon. You tend to get a lot of gases in the nonmetals, but that's not always true. Carbon would be a solid material. Sulfur and phosphorus would also be solid elements when we're talking about room temperature, STP, standard pressure and temperature. So what differentiates these besides the location where they are on the periodic table? That's what we want to ask ourselves, right? So if I take a look at metals, what would I consider in terms of a good list? All right, now I have the periodic table up here, so I would suggest if you are studying or you're using this video to study, grab an index card or a sheet of paper so that you can go over this list and you can take some notes down here. All right, so in terms of metals, we would first of all classify a metal as something that is lustrous, and that would mean that it's shiny. All right, so if you think about most metals, not all of them, but a lot of them, they tend to have a shiny hue to them when you're working with them. Most metals are going to be good conductors of both heat and electricity. So you think of some common examples like iron, a iron frying pan, or copper wiring, which is used for electrical conductivity, right? All of the metals tend to be very good conductors, both of heat and of electricity. When you take a look at their boiling points and their melting points, they tend to be pretty high. In fact, all metals, except for one, are solid at room temperature. And that one that's the exception is number 80. You can see it down here, and that would be mercury. So number 80, right here, would be mercury. Okay, that's a liquid at room temperature. So if we're taking a look at that, high melting points, high boiling points, we tend not to be able to melt these metals very readily at slightly above room temperature. We're talking about very high melting points. They also have high density. So a lot of these impressive physical properties that we see with the metals, most metals tend to sink. They're not going to float very readily when you put them into water. Some people will ask about, well, then how do you build, an iron ship that can float and things like that? You have to talk about buoyancy. That's a physics concept that you could head over to the physics lectures and take a look at that. But in overall, we're looking at high density when we're talking about metals. Metals are malleable. Okay, so if you take a look at that word, malleable means they're able to be shaped and sort of hammered or bent into a specific form. They're not very brittle. They're not going to just crumble or break apart for the most part if you're trying to work with them. Now again, mercury being a liquid, it tends to be sort of amorphous and it'll occupy whatever container you're working with. But by and large, when you're dealing with the solid metals, some of them will be harder than others, but they usually are malleable if you heat them up enough. Now, some of the chemical properties, okay, because we were just talking about physical properties, some of the chemical properties of metals is that they lose electrons very readily. In fact, all metals are going to be considered a good reducing agent. They're relatively low in their electronegativity. If you need a refresher in electronegativity, there's a lecture involving the periodic trends, so that's ionization energy, electronegativity. So head over there if you're confused about what that is after this lecture. And the biggest thing here is they lose electrons. Now, a lot of students get confused when we talk about losing electrons because they tend to associate a loss as something negative, right? If I tell you that I've lost money in my bank account, I would expect a negative balance to be reflected there. But when we're talking about electrons, the charge is what we're really working with, and electrons carry a negative charge, right? So let me switch colors here just for a second. Let's use red. Okay. So when we're looking at this, if I have, let's say, sodium, that's a very common metal. Sodium, when it loses an electron, we write it as Na+, not Na-. And that's because when we're talking about the charge, an electron carries a negative charge. So to lose an electron means that I have one additional proton in the nucleus relative to the electron balance. And so I get a positive charge when I lose electrons. So all of this, to circle back, is to say metals, whether it's lithium, sodium, iron, cobalt, okay, they all have positive charges associated with them when they are going into any sort of an ionic form. Now, you can find these in their elemental form. So, for instance, you could find iron that doesn't have any sort of ionic charge. It's just solid iron. But if you are going to give away electrons when you're dealing with metals, they're going to take on positive charges. So you should not see any metals that contain negative charges. That's not in their behavior, their chemical behavior. All right? So we're going to talk about the nonmetals now. And as you would expect, it's mostly going to be the opposite of the metal list that we just covered. So, and then we'll briefly talk about metalloids. They're, again, a small class, so we're not going to spend quite as much time on them. The nonmetals, in contrast to the metals, first of all, they're very dull in their appearance and their, I don't necessarily want to say their color. Sometimes they can have vibrant colors. But they're very dull in their appearance. They're not shiny. They're not lustrous like the metals are. They tend to be pretty plain. They are poor conductors of electricity. So when you are dealing with any sort of a non-metal, it's usually not going to conduct electricity well. It's also not going to conduct heat very well. That's the responsibility of the metals. And in fact, if you're ever in a swimming pool and a thunderstorm comes and they say everybody needs to get out of the pool, it's not necessarily the water that is the concern when you're talking about electrical conduction. It's all of the metallic ions that are found in the water. It's the magnesium, it's the sodium, it's the calcium. All of those metal ions are what are really responsible for conducting the electricity and makes it, you know, unsafe when you're dealing with that sort of stuff. So nonmetals are poor conductors of heat and electricity, and in relative contrast to the metals, they tend to be very brittle. So if you try to work with them, certainly the gases aren't going to have much shape at all. They're just going to occupy whatever container they're in. But let's say I'm dealing with solid phosphorus or carbon, right? Think about, here's a good example. Carbon, right, is charcoal. So that's one form. Carbon has many forms. You could also talk about it as a diamond, in which case it would be very difficult and rough to work with. However, graphite or charcoal, like you would light your grill with, is also nothing other than carbon. And if I take a hammer to a piece of charcoal, it's very brittle. It's going to flake or break apart very easily when I try to work with it. It's not going to be able to be bent into certain shapes and hold that shape after I've worked with it. So they're not particularly malleable. All right, most of these compounds have lower melting points and boiling points. And that's, of course, very evident because we have a lot of gases. Oxygen is a gas at room temperature. Fluorine, chlorine are gases at room temperature. Bromine is a liquid at room temperature. So you have a lot of these, and certainly all the noble gases, you have a lot of these gases over with the nonmetals at room temperature, which means it would have to get colder than room temperature, and in some cases quite a bit. Like liquid nitrogen, you have to go far below room temperature in order to achieve even a liquid state. Alright, so we're talking about the melting points, the boiling points. Those are going to be on the lower end. It's going to be easier to get things to melt and boil when we're talking about these types of elements. And again, I will mention these are solids, liquids, and gases when we get to the nonmetals, whereas the metals were almost all solid except for one, which was mercury. That was a liquid. So here we've got a good variety. We've got some solids, We do have some liquids, and in fact I should say liquid because it's bromine. Bromine is the liquid. And then we do have gases. All right, now in terms of their electrons, most of the nonmetals are going to have a tendency to want to gain electrons. Now, electron loss or gain is all about trying to get into the configuration of a noble gas. So the metals, which we saw over on the left side of the table, they were ready to lose electrons so that they could retreat back into the previous row and obtain the electron configuration of the previous noble gas. When we start looking at these nonmetals, let's take sulfur for instance. If I take a look at sulfur here, sulfur only needs to gain 2 electrons in order to have the electron configuration of argon. So it's going to more readily pick up 2 electrons than it is going to attempt to get rid of 6 electrons and retreat all the way back to neon. So when you deal with most of these nonmetals, they're going to have negative charges, meaning they're gaining electrons, and they can be anywhere from 4 to 8 electrons, with 8 being the full octet. Everybody's heard of the octet rule usually. 8 being the full set that we're working with when we are looking to gain all of the stability in the valence shell. All right, these groups have high electronegativity. Now, I mentioned this before with the with the metals. High electronegativity, if you look at the term electronegativity, it's basically the ability to hold on to electrons once you have a hold of them. Okay? Now, it would make sense that these nonmetals are going to have high electronegativity. If they get a hold of an electron, they're going to hold on to it for dear life because they want to get closer to the noble gas configuration. The metals, on the other hand, are looking to get rid of some electrons so that they can retreat back to the previous noble gas electron configuration. So it would not be beneficial for metals to have high electronegativity. They're looking to let go of their electrons. They do not want to hold on to them. All right, now, just as the metals were good reducers, the nonmetals are going to be good oxidizers, and we can see that quite easily when you think about things like oxygen. Oxidizers tend to be found in the nonmetal portion. Okay, now, we did mention a little while ago these ideas of shells, and so let's switch the color up here again. You can have S, P, D, and F shells. Let's do purple. So the S shells involve the first 2 rows right here. These are the S shells. And the S shell can hold 2 electrons at most. Okay. Now, when you have the transition metals down here, these guys occupy, that's that light blue color down here, these guys occupy the D shells. Okay? And the D shells can hold up to 10 electrons. And what I'm writing here, in case people don't realize, it's E with a minus charge. Okay, so that represents electron. So we've got the D shell. I'm going to take a trip down here. These right here, the lanthanide and the actinide series, are the F shells. The F shells can hold up to 14 valence electrons, so they are quite impressive in terms of their capacity. Okay, and then finally, up here, this is a mix of metals and nonmetals, but a lot of these over here are the nonmetals, starting with boron and going over to the noble gases. Okay, those are the P shells. And the P shells can hold up to 6 electrons. So if you come across this and you hear S, P, D, those shells that sort of ring a bell from, back when you were taking chemistry, we're talking about the valence shell that we're currently filling. You can have S, P, D, and F. We're not going to get into it in this lecture, but they do have different shapes. So the S tends to be a spherical, like orbital shape, whereas the P look like dumbbells or figure eights, and then the D and the Fs get much more complex in terms of their sort of balloon structure that they have. So the last thing I just wanted to mention, this is going to be pretty quick, but the metalloids, the ones that come down in this row here. The metalloids are considered semiconductors. So they have some properties of metals, some properties of nonmetals. They really fall into kind of a gray area when you're dealing with them. Again, boron, silicon, germanium, arsenic, antimony, all of these are good examples of metalloids. Sometimes you get debate over which ones are metalloids and which are not. Gallium is kind of interesting. So gallium over here in spot 31. Okay, gallium will actually melt in your hand. It melts at about 30 degrees Celsius. So room temperature, for those that don't know, is about 25, somewhere between 22 to 25, depending on how you like the comfort of your room. Okay, and then you put it into the palm of your hand, and gallium will melt from a solid to a liquid. So you're starting, as you approach aluminum, gallium, some of these, you're starting to approach a little bit closer towards the non-metal behavior, but there's enough of the metallic, you look at aluminum, you would still classify that as a metal. So they're starting to dance around the border of the metalloids. Again, the metalloids are going to have melting points and boiling points that are in between. They won't be as high as the metals, and they won't be as low as the nonmetals. So you wouldn't expect many metalloids to be gases at room temperature or anything like that. And their biggest property is that they are called semiconductors. So they're okay at conducting heat and electricity, but they're not nearly as phenomenal as the metals are. Okay. So let's take a look at some of these groups here. Okay. So if we take a look, the first group that we've got is the alkali metals. So the alkali metals are in group 1A over here, and when we take a look at the alkali metals, they have a charge associated with them. They have a charge of 1+. Okay? So hydrogen, lithium, sodium, potassium, all of those have a charge of 1+. Now, these metals tend to be soft, so you can cut them with a butter knife. They're very, very peculiar in terms of their solid nature. They're very soft metals. Not all metals are hard metals like iron or something like that. They are highly reactive, the alkali metals are. They usually are stored in oil. So if you're talking about not sodium chloride like table salt, but actual sodium metal, they tend to store lithium, sodium, potassium, these metals, under oil because they will very readily react with any moisture that's found in the air, and they will quickly and rapidly degrade in that case. Sodium is the most abundant out of this group. It is certainly needed in terms of the human body and biochemistry. Now, we wouldn't be taking solid chunks of sodium, but the sodium metal or electrolyte is very important, followed by potassium and lithium, and then some of the other ones further down like rubidium and especially the francium. They are more difficult to come by. Francium, especially because of its radioactivity, is difficult to find in nature. So you're going to find a lot more in terms of the lithium, sodium, and potassium, especially sodium and potassium tend to be very abundant in comparison to the others. I will note that hydrogen here tends to be grouped and lumped as a non-metal. There have been studies that show when the temperature gets very, very, very low that hydrogen will have some metallic behavior. However, it is usually classified, because it's a gas, as a non-metal, and it does behave as a non-metal at room temperature. So we sort of exclude hydrogen from this group as far as its metallic properties are concerned, but hydrogen does take a 1+ charge on anytime we're dealing with it. And then we come to the alkaline earth metals, which is, and by the way, just to show you guys, I am working with the list that we had up here. So I'm doing alkali metals, and now we're talking about alkaline earth metals. We're going to go through these somewhat briefly. Okay. So if I take a look here, the second group is the alkaline earth metals, and this is group 2A, and it has a 2+ charge associated with it. So that means you would come across calcium 2+, magnesium 2+ in their ionic form. They give up 2 electrons from their valence shell. And when we're dealing with these, some of the common ones, again, that I just stated are calcium and magnesium. You do have barium and radium. Those, again, are a little more difficult to come by. Calcium, which is very important for bone development, and in fact, that's why X-rays show up the way that they do, is because calcium is a metal. when you look at it. And so X-rays will pick calcium up. That's why you can take an X-ray and you see the bone structure when you're working with any sort of X-ray material. So then we have the transition metals that come after that. This is, again, the large group that's in between here with the blue. You can see starting with the scandium all the way up to the zinc in shell 3D, and then yttrium all the way to cadmium, and so on and so forth when you're dealing with these transition metals. The transition metals can have multiple charges. Okay, so this is sort of a question mark. They will always have a positive charge, but you can have what's called more than one oxidation state. Okay, manganese, number 25, is very well known for this. It can have oxidation states up to 7+, and they can range all the way from 1+ to 7+. You can take on multiple charges. Iron can be iron 2+ or iron 3+. You can have multiple charges on copper. So this is a very common occurrence where we get multiple charges. I would not spend your time sitting and memorizing all of the different oxidation states that these can have. I would simply suggest that you realize they can have multiple oxidation states, and that they would, in particular, always carry a positive charge with them. You're not going to see, again, any metals with negative charges. Okay? So those are the transition metals. Transition metals can range in terms of their rarity, so some of them are very common. For instance, iron is a very, very common transition metal. So is chromium, and so is copper and zinc. Again, all of these are important minerals in the human diet, so you're going to want to make sure that you know some of the more common ones, especially if you're studying for the MCAT. And then you still have some of the precious metals that aren't quite as common here. Silver, for instance, number 47, Ag, that's silver. You also have gold below that, 79, which is Au. Platinum, 78, which is Pt. Okay, and then there's some other ones that are sometimes used in reagents in organic chemistry. So, for instance, osmium, number 76. There's a reagent that uses osmium in order to perform oxidations on double bonds. So they have a large range in terms of their versatility and their use, but these guys are all going to be classified as metals. And that would bring us down to the slightly rarer set of the Lanthanide and the Actinide series. You, again, can find uses for these. However, most of these, because of their rarity and just the common use of transition metals and the other elements in comparison to these, you're probably not going to come across these quite as often. But they are important down here. Again, remember, these are in the F shell, okay, and these would also have a range of different charges that they could take on, similar to the transition metals. Okay, so then that brings us to group 3A. We're still working with the metals, however, boron is now considered a metalloid for sure in this group, with some other ones that might be slightly questionable. In group 3A, and notice that the transition metals are group B, right? So we have 3B, 4B, 5B, so on and so forth, and then we have 1B and 2B as we come over here to copper and zinc, and then we go back to A, similar to the alkali metals and the alkaline earth metals. And so when we get here, we've got 3+ for group 3A. Now, when you get to group 3A, these are some of the metals that are starting to get closer to the metalloids, like aluminum. We talked about gallium earlier, how it can melt in your hand because it only needs a slightly warmer temperature than room temperature to melt. But these, by and large, are still all going to act metallic when you come across them. And then we start crossing over the metalloid line. Group 4A is an interesting group because we have a mix of all three. So group 4A is also unique because you can have 4+ or 4- depending on what you're working with. So the oxidation number here is going to depend on what you are currently bound to. Now certainly the metals, for instance tin, number 50 down here, that's a metal. So tin is not going to have the negative charges. Tin would have the plus charge when you're working with it. But carbon, for instance, could be 4+ or 4- in its oxidation number because it's going to depend on what carbon is bonding with. If carbon is bonding with something like a metal, then you're dealing with carbon that's going to have a negative oxidation state. Whereas if carbon is bonding with another nonmetal, for instance, oxygen, which is more electronegative, CO2, carbon dioxide, then carbon is going to contain the positive oxidation number. So this is an interesting group because you can have 4 plus or 4 minus. Silicon and germanium are in the metalloid category, and then carbon is a nonmetal, with tin and lead certainly being metals. This next group over here in the nitrogen family, you're going to have 3 minus. So a lot of students want to put 5 plus there. That's not going to be 5 plus. That is going to be 3 minus because you're looking at picking up 3 electrons to get to neon, or phosphorus would be looking at picking up 3 electrons to get to argon, so on and so forth. So then we have the oxygen family, which is 2 minus, okay, and the halogens, which would be 1 minus. Before we get to the noble gases do not have a charge, so we're going to put a null sign there. Now, when you're working with these, the electronegativity is going to increase as we go across here. So that means as we get closer to becoming, and I'm going to put En for electronegativity, okay, En is increasing this way. So as we get closer to a noble gas, right, here are the noble gases, this is what we're aiming for. As we get closer to the noble gases, you're going to want to pick up electrons more and more. So think about it from this top row here. Here's nitrogen. Nitrogen is 3 electrons away, right? So it's a little far from becoming a noble gas, but it still has enough distance there that it's going to pick up some electronegativity. Then oxygen is only 2 electrons away from becoming neon. So it is going to be more aggressive in terms of its ability to pick up and hold on to electrons. And then fluorine is only 1 electron away from that goal. So think about it as you get closer and closer to the goal, right? Nitrogen is the furthest from its goal right now, as far as the nonmetals here. Oxygen is getting closer to that goal, and fluorine can see the light at the end of the tunnel. It's almost there. So its electronegativity is the highest because it's just out of reach. It's that final push, that final mile to get that last electron. So fluorine would be the most electronegative. And in fact, fluorine is the most electronegative element. Again, we'll talk about electronegativity in the proper electronic trends video, the periodic trends. So that pretty much covers what we want to look at in terms of charges, electronic charges, the properties of metals and nonmetals, the different shells that we would take a look at, and some of the basic properties that you would come across in these various groups. Okay? So what I'm going to do here is I'm going to scroll down, and I have a set of questions for you to practice. So the first one is, which element would conduct heat the best, iron, carbon, or chlorine? Number 2, provide an example of a metalloid. And number 3, what charge would you expect sulfur to carry in its ionic form? All right, so that's what we're working with. And you want to answer these, pause the video, and then come back and we will finish these up. Alrighty, hopefully you had a chance to give these a shot. If not, again, please pause the video and try them first. So, in the first question, which element would conduct heat the best? We have iron, carbon, and chlorine as options. And the option that would suit us best, let's use red for our answers here. The option that would suit us best is going to be iron. That's because iron is a metal, whereas carbon and chlorine are nonmetals, and carbon being a solid, chlorine being a gas. Okay, carbon would probably be slightly better at conducting heat than chlorine would be. However, iron is certainly the best choice here as a metal. The metals are good conductors of heat and electricity. So the next question was, provide an example of a metalloid. There are lots of different options that you could have used here. So I will write a few of them. Boron would be one option. That's a B, okay, for boron. Silicon would be another option. You could also have germanium. Okay, and there are several others. You could also have arsenic. And you could use antimony, which would be SB, or tellurium, which would be TE. Now, The last question says, what charge would you expect sulfur to carry in its ionic form? If you were to look at the periodic table, the sulfur is in the oxygen family group, and that carries a charge of 2-. So you would expect an ionic charge of 2- on sulfur. So hopefully you guys found this video helpful in terms of your studying and your content. This will conclude the lecture on the periodic table of elements and the properties of metals, metalloids, and nonmetals. Thanks, guys.